Hi everyone, this is Professor Fernandez. We're doing class notes A in lesson 4. In this example, we are considering a mass on a spring, and we're going to try to find out what its spring constant is by knowing what the length that the spring stretches by is after we put a mass on it. So the first thing I'm going to do is I'm going to draw the spring in its equilibrium position without a mass on it. And then in this example, we're going to put a mass on it. And that's going to stretch the spring down a little bit. This is a 1 kilogram mass, and it stretches the spring down by some amount L. Okay? And we're told what L is. That's the 49 over 320 meters. You'll see why that number is so strange in a minute. So what we need is some way to connect the fact that the mass's length has changed with what it changed as a result of, which is putting the weight on the spring. And the model that connects that, I'm going to scroll up here, is Hooke's law. So we are going to use this part of Hooke's law, the part that tells us that the magnitude of the spring restoring force is KL. Great. And then we're going to use balance of forces, so effectively Newton's second law. So if I go back down here, what's happening here, if I do our little free body diagram here, so the restoring force is pulling the spring up. The spring literally wants to restore to its initial equilibrium state. However, the weight of the mass, its mass times the acceleration of gravity, is pulling the mass down. And there's going to be a balance of forces here between these two, like a tug of war. And when the spring comes to rest, these two forces will be equal. So the restoring force will be equal to the mass times the acceleration of gravity. And because Hooke's law tells us that the restoring force is the spring constant times the length it stretched, then we have this nice little relation between these four parameters. In this particular problem, we are asked to find the spring constant. So we are going to solve for K to get mg over L. And then now it's just a matter of substituting in what we know. So we know that this is a 1 kilogram mass, and all the units are in SI, so meters and kilograms. So we're going to use gravity in meters per second squared. I'm just going to do 9.8 for that as a rough estimate of the acceleration of gravity, and then we will use this quantity for L. Okay. So this is the reason that I chose all these problems, all these numbers, because this arithmetic turns out to be 64, which is a nice number and not any decimals or fractions. And the units of K are useful to know. You can tell that from this version of K. So mg, this is mass times acceleration, that's a force, so the units of that is newtons. And L, this is a length, so the units of that in SI units is meters. So K's units are the ratio of those two, Newton per meter. Okay, so we found our K value, and that's all that we wanted to do for this particular problem.